So I wanted to start the hour with this example, once again, to kind of wrap a bow around the idea that changing basis can help us in not just a situation where we're looking at our vector space being R2, R3, or whatever, but also here's another example of a question that came up in an abstract algebra course that required us to change a basis between this basis of square roots, 1, square root of 2, square root of 5, square root of 10, I call that the B basis, and the basis which consists of the powers of their sum. So square root of 2 plus square root of 5 raised to the power of 0, 1, 2, and 3. So if we call these original vectors E1, E2, E3, E4. So if that's the basis of the B basis, then the question is, how do we find a matrix that converts from A coordinates into B coordinates? And to figure that out, we need to answer the question, how can we write 1, the first basis vector of the A basis, so let me call that something. Let me call these vectors maybe F1, F2, F3, and F4. And again, I'm only calling them vectors because I'm thinking of them as being participants in a vector space. So then, how do we write F1, F2, F3, and F4 in the B basis? So in terms of E1, E2, E3, and E4. Yeah. 1, 0, 0, 0, right. So the first basis vector in the A basis here has coordinates in the B basis 1, 0, 0, 0, because 1 is equal to 1 times 1 plus 0 times the square root of 2 plus 0 times the square root of 5 plus 0 times the square root of 10. So there's our first basis vector. The second one should also be relatively straightforward. Square root of 2 plus square root of 5, what does that look like in coordinates in the B basis? So how many 1s, how many square roots of 2, how many square roots of 5, and how many square roots of 10? And the reason this is different in abstract algebra, is that we want these coefficients all to be rational numbers. So I'm going to take 0 1s, and how many square roots of 2? 1 of them. And square roots of 5? And square roots of 10? 0. So the coordinates of square root of 2 plus square root of 5 in the B basis are 0, 1, 1, 0. So far, so good? So now the question turns to, if I've got the square root of 2 plus the square root of 5 squared, so that's the third basis vector in my A basis, how do I write that in the B basis? So what did you do to answer this question?
You gotta distribute the square.
Distribute the square. What do you get when you distribute the square?
2 plus 5.
2 plus 5. But plus, remember the sum of a square is not the same as the square of the sums. Right, that there's a term in the middle. Square root of 2 squared plus square root of 5 squared plus 2 times square root of 2 times square root of 5. This is just the old binomial theorem. X plus y squared is x squared plus y squared, but also plus 2xy. So actually, when I simplify this expression...
Why do you have a 2 in front of the square root of 2 and square root of 5?
Yeah, why do I have a 2 in front of the square root of 2 and square root of 5? This one, you mean?
Yeah.
So again, let's just imagine that we, instead of squaring, multiplied this out using FOIL. When I, quote, FOIL this out, I'm going to get 2 from my first product, I'm going to get 5 from my last product, but then both the outer and inner products, the O and the I in FOIL, both of them give me the same square root of 2 times square root of 5. And so in total, I end up with a pair. So when I multiply out this square, what I get is 2 plus 5, so 7, plus 2 times square root of 2 times the square root of 5. So 7 plus 2 radical 10. What does that look like in coordinates with respect to the b basis?
0, 0, 0, 2.
So I have a 2 in my square root of 10 component. Where does that 7 go?
Oh, to the top.
Yeah, there we go. So there's the coordinates of f3 with respect to the b basis. So in other words, when I take the square root of 2 plus the square root of 5 quantity squared, the result is 7 times 1 plus 0 times square root of 2 plus 0 times square root of 5 plus 2 times square root of 10. So there are the coordinates of f3 in the b basis. And finally, f4. I'm going to borrow our answer from f3 to figure out what f4 is. Square root of 2 plus the square root of 5 quantity cubed. That's going to be the square root of 2 plus square root of 5 multiplied by the square root of 2 plus square root of 5 squared, which we just figured out was 7 plus 2 square root of 10. So I'm just going to save ourselves a step when we cube this and put in the square here. And let's FOIL this out and see what we get. The product of the first terms is 7 times radical 2. The product of the outer terms is the square root of 2 times the square root of 10, which is the square root of 20. But how can we simplify the square root of 20? 2 times the square root of 5. Yeah, it has a factor of 4 under the square root, which when we pull out becomes a 2. So that's 2 times square root of 5. That saves our bacon here. Otherwise, we couldn't find the square root of 20 in our b basis, so it wouldn't have worked. But because we can simplify it, we can find it as a factor, a multiple of the square root of 5.
2 times 2 is square root of 2 times 2 is square root of 2.
So let's take that again. So we had square root of 20.
Well, you just had,
You but 2
you
minus
just
square root
had
of
2 in
20.
front.
Oh, you're right. I'm sorry. I missed that too. My fault. So it was 2 square root of 20. Thank you. And square root of 20 became 2 square root of 5. So in total, we end up with 4 square root of 5. Thank you. 4 square root of 5. There we go. So that's from the outer product. The product of the inner factors is 7 square root of 5. And finally, the last square root of 5 times 2 square root of 10 is going to give me 2 square root of 50. But the square root of 50 simplifies because it's got a factor of 25. It's 5 square root of 2. So this becomes 2 times 5 square root of 2. Oops. So it becomes 10 square root of 2 as our last term. And we can combine the like terms in the middle. 4 square root of 5 plus 7 square root of 5 becomes 11 square root of 5. And the terms on the outsides, 7 square root of 2 plus 10 square root of 2, 17 square root of 2. So when all of that dust settles, F4 rather, our fourth vector in the A basis, has B coordinates 0 times 1 plus 17 radical 2 plus 11 radical 5 plus 0 radical 10. Ugh. So with these 4 vectors, we can build a matrix with those vectors as columns. So let's write that out. First column 1, 0, 0, 0. Second column 0, 1, 1, 0. The third column 7, 0, 0, 2. And the fourth column 0, 17, 11, 0. And my question to you is, what does multiplication by this matrix do?
Gives you what? Yeah, something else.
Yeah, which basis, I guess what I'm asking is, which basis does it convert from, and which basis does it convert to?
Converts from A to A.
Converts from B to A? Actually, I think it's the other way around. be. So let me just show you why. Let's suppose that I multiply this by something which is in the A basis, like 0, 1, 0, 0 in the A basis. 0, 1, 0, 0 in the A basis corresponds to the number square root of 2 plus square root of 5. Right? 1 times square root of 2 plus square root of 5 plus 0 times the other entries in the A basis, which are the other powers of square root of 2 plus square root of 5. But if I multiply this matrix by 0, 1, 0, 0, the result is, well, since this is a standard basis vector, we're taking the linear combination of 0 times the first column, 1 times the second column, 0 times the third column, and 0 times the fourth column. So the result is just the first column of that matrix, 0, 1, 1, 0. And if these really are B coordinates, then when we impose our context on them once again, we have 0 times 1 plus 1 times square root of 2 plus 1 times square root of 5 plus 0 times square root of 10. And so we are indeed talking about the same thing, square root of 2 plus square root of 5, in both cases. So in other words, this matrix that we built by converting the F basis into the A basis into B basis coordinates, that matrix gives us the transformation from A coordinates to B coordinates. So anything which I have written as a sum of powers of square root of 2 plus square root of 5, I can use this matrix to convert into square roots of 2, square roots of 5, square roots of 10. So that's what this matrix has the power to do. So how does this change of basis matrix help us to answer this question? How do I convert the golden ratio into A basis? Actually, this is written wrong, isn't it? I really wanted what are the A coordinates, not the B coordinates. The B coordinates are obvious. Find for me the A coordinates of the golden ratio using this matrix. So how do I do that? Given that this matrix's job is to convert A coordinates into B coordinates. Last time we said that we could rewrite this as 1/2 times 1 plus 1/2 times the square root of 5. So which coordinates of this golden ratio do we know based on that writing? Do we know the B coordinates? Are the B coordinates easier to find from this expression, or are the A coordinates easier to find?
B.
The B coordinates, because we've written it as a linear combination of 1 and square root of 5. So let's write down the B coordinates of this golden ratio. What are they?
And 1/2 plus
1/2.
square root of 5 over 2.
Square root of 5 over 2, so I'm going to have a 1/2 in the square root of 5 entry, right? Because remember, the B basis is 1 square root of 2 square root of 5 square root of 10. So I have 1/2 times 1 plus 1/2 times square root of 5, but I don't have any square roots of 2, and I don't have any square roots of 10. So there are the B coordinates of the golden ratio. Now we just want to know what are the A coordinates. So what's my job? Yeah. We either need to find the inverse of this matrix, and that would be a change of basis matrix that can take us from B coordinates to A coordinates. Or we could just row reduce. It depends on how much we'd like to be able to do this with other numbers written in the A basis as well. Okay. Let's find the inverse, just because it's one of those great character building exercises to have to do row reduction to find the inverse of a matrix. So I'm just going to, for a moment, take all of this other stuff here and get rid of it. And let's go about the process of finding the inverse of this matrix. How shall we find the inverse of a 4 by 4? What is your preferred method?
I would use the first column
Yeah, let's do row reduction, because the other option for a 4x4 would be to try to compute its adjugate and divide by its determinant, but that would require us to do 16 3x3 determinants and one 4x4 determinant. So, let's row reduce. Shouldn't take too many steps because we do have a lot of zeros already to start with. In fact, we already have one pivot in here. So the process isn't too bad. So after our first row operation, we've cleared out that third row. And does anyone see the step that I can do to this to now put my matrix on the left into its row echelon form? I've identified two pivots, but how can I, using one step, identify the other two?
Just switch the two.
Switch these two rows. Swap them out. If I swap those two rows out, there's the result of switching the two rows. So row 3 swap with row 4. Now we have all of our pivots. And now it's just a matter of clearing out everything above and below those pivots, and we will have our inverse. So let's divide the third row by 2 and the fourth row by -6. So now all our pivots are equal to 1. And now to finish, we just have to subtract 7 times the third row from the first row. So row 1 minus 7 row 3. As well as subtract 17 times the fourth row from the second row. And we're done. The matrix on the left is now the identity matrix. So now that we have our inverse, let me put a nice bracket around it. So there's our inverse. So this should be the matrix that converts us from B basis into A basis. This is what we wanted, because we knew what the golden ratio was in the B basis. Namely, in the B basis, the golden ratio was 1/2 times 1, plus 0 times square root of 2, plus 1/2 times square root of 5, plus 0 times square root of 10. So just to reiterate here, this is 1/2 plus 1/2 square root of 5. And now we will get our A coordinates, which is what we wanted, by just performing this matrix product. And all in all, we end up with 1/2 times the first column, so 1/2 0 0 0, plus 1/2 times the third column, 1/2 of 0, 1/2 of 17/6, 1/2 of 0, and 1/2 of -1/6. The A coordinates of the golden ratio are 1/2, 17/2, 0, -1/12. Sorry, 17/12, -1/12. So for you to check, if you don't believe this manipulation, just check that when you take 1/2 times 1 plus 17/12 times the square root of 2 plus the square root of 5 plus 0 times square root of 2 plus square root of 5 squared minus 1/12 times the square root of 2 plus the square root of 5 cubed. Try that sometime and verify that the result of that computation is 1/2 plus 1/2 square root of 5. But we're still talking about the same number, the golden ratio. We're just talking about it in two different coordinate systems. In the first case, we're talking about it in the coordinate system that's based off of the square roots of 2, 5, and 10. And in the second case, we're talking about the coordinate system which is based off the powers of the sum of square root of 2 with square root of 5. And in our Abstract Algebra 2 class, the purpose of a computation like this was to show that any vector space which is built out of one of these bases is exactly the same, is equal to, set by set, is equal to the vector space that's formed out of the other bases. So these bases describe the same vector space, which is not obvious in the beginning. But if we can show that there is an invertible change of basis matrix that takes one into the other, then those vector spaces have got to be exactly the same. Which was a big result for us in abstract algebra 2.